Okay, so in the last class we were discussing that what is the role of sensitivity in uh, robustness study against parameter variations. So we saw that sensitivity, uh, the peak of the sensitivity plot or the or MS should be as small as possible in order to have good robustness against parameter variation. And also we discussed that if there is unstable pole as well as non-minimum phase zero in the plant, and if they are and in particular if they are very close to each other, then high peak in sensitivity plot, that means large ms is unavoidable using LTI controller. Okay, so also I said that gain margin, phase margin, mm, mm, gain margin, phase margin are not good indicator against robustness always. It may happen that uh, for a system, for a feedback system, gain margin, phase margin are good, but your MS is small. As a result, if there is a little perturbation in the system or parameter variation in the system, then the system may become unstable. Okay, that so one such case we will consider. So, an example where gain margin, phase margin are good. So what is a good in phase margin means what? So gain margin, phase margin good means a uh, gain margin greater than equal to 6 dB plus minus 6 dB. Plus minus I am saying because positive gain margin and negative gain margin. Positive side or upper side gain margin and lower side gain margin. So upper side gain margin 6 dB plus 6 dB. That means 6 dB means gain you can multiply, gain 200% increase of gain you can make, and uh, your mm, uh, and uh, uh, and minus 6 dB gain margin means gain you can reduce by 200%. Okay, so suppose your gain is 1, so plus 6 dB gain margin plus 6 upper side gain margin plus 6 dB upper side gain margin means you can make it 2 up to 2. Again you can increase up to 2, and minus 6 dB lower side gain margin means gain you can reduce by a factor of 0.5. Okay, that means gain you can reduce up to 0.5. Okay, so plus minus 6 dB gain margin is a that's why it is considered as a good or reasonable gain margin for practical system. And phase margin, I think you know this, that phase margin for a system for a good design should be greater than equal to 30 degree, because phase margin is closely related to your damping ratio of the system, and phase margin equal to your damping ratio is approximately equal to phase margin divided by 100 approximately. So if you can for a good design, your your damping should be greater than equal to at least zero point 0.3, in between zero point 0.3 to zero point 0.8 or zero point 0.7. Okay, so that's why your phase margin should be greater than or equal to 30 dB. Okay, so for a good design, gain margin should be greater than equal to plus minus 6 dB. That means positive side plus 6 dB and negative side at least minus 6 dB, and phase margin should be greater than equal to 30 dB. So now we will see, in spite of having good gain margin, phase margin, a system may be prone to instability. Prone to instability means it may exhibit low or low MS. Sorry, it may exhibit a poor poor sensitivity, and that's why it is uh, uh, there is poor robustness. So even if the gain margin, phase margin are good, it may suffer from poor robustness, because you will see that MS or sensitivity peak is high. Okay. So such a system, practical system, is this one. It is a transfer function of a flexible structure, flexible space structure, that is satellite that satellite system, satellite those yeah, solar panel. Solar panels are very flexible. Okay, so but satellite structure, that is solar panel orientation control. If you do that, uh, the transfer function will will come out to be like this. Okay, there is a flexible structure. Any flexible structure, flexible beam, or 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 that kind of system will have mm, this kind of transfer function. So if you see this kind of system, and if you see gain margin and phase margin, if you just close the loop, and if you want to verify gain margin, if you want to check what is gain margin, phase margin, then you can see from this figure I have drawn this. And the plot will be like this, and the phase margin is 70 degrees. That means it is good, and you can easily see from the figure that both upper side and lower side gain margin are, upper side gain margin is infinity and lower side gain margin is zero, because it is a arbitrary small, it is a stable system. Stable means s equal to zero, pole is there, that means gain you can reduce arbitrarily to small value. So that means negative side gain margin is also approximately zero, or very close to zero, and upper side gain margin is infinity. That is very good gain margin, phase margin. But you can see that MS, you can easily check that sensitivity plot. If you do that, means that plot of S j omega equal to 1 by 1 plus L j omega, that magnitude plot if you do, and if you see the peak value, that means MS will come out to be 3.67, that is much greater than 1. Okay, as a result MS inverse is very small. So as a result, what will happen, this point, you can easily see from this figure that this point is very close to -1, although its gain margin, phase margin is good. So that's why if there is some perturbations in the system, maybe because of parameter variation, or maybe because of neglected dynamics or something, type of uncertainties, uh, uh, then what will happen? This point will touch -1 point easily, and because they are, because the distance between -1 point and this point is only 0.272. So that's why this system is very I mean system suffers from poor robustness. So this is the conclusion, that phase margin, gain margin may be good, but the system may have poor robustness, because MS is high. So that's why MS is a very good indicator for uh, robustness. We'll see that now the question may be like that, that we have seen that uh, that it may happen that MS is small, but gain margin, phase margin are poor, right? So we have to now guarantee that if MS is small, then we can also ensure the gain margin, phase margin are good. That means small MS, small peak in the sensitivity plot will also guarantee good gain margin, phase margin. That we'll see. That means relation among gain margin, phase margin, and MS. So this is the relation. This relation we will derive soon, but for the time being, I am just writing. So maximum GM max means upper side gain margin. Upper side gain margin is always greater than, or so these are the inequalities that you can prove. Upper side gain margin is greater than equal to MS by MS minus 1, and phase margin is greater than equal to 2 sine inverse 1 by 2 ms. Similarly, for lower side gain margin also inequality is there, that I will come later. Okay. Suppose you want to ensure, as I said, we always, for a practical system, we want gain margin max or upper side gain margin is greater than equal to 6 dB, that is greater than equal to 2, and phase margin greater than equal to 30 dB. Then what should be the value of ms which will guarantee these two? You can easily see that if you want to guarantee gain margin max greater than equal to 2 means ms by ms minus 2, ms minus 1 should be greater than equal to 2. This means your ms is less than please. So whose phone is ringing? Hello, whose phone is ringing? Please keep it in silence mode. Okay, so as I was discussing that ms by ms minus 1, we want to ensure that gain margin max greater than equal to 6 dB. That is gain margin max greater than equal to 2. So how to ensure that? So gain margin max greater than equal to 2, you can ensure uh, if ms by ms minus 2 is gain margin greater than 2 means what? Gain margin greater than 2, you can ensure if ms by ms minus 2 1 is greater than equal to 2, which leads to ms less than equal to 2. On the other hand, if you want to guarantee phase margin greater than equal to 30 degree, then from this relation this should be greater than equal to 30 degree. That is 2 into sine inverse 1 by 2 ms should be greater than equal to 30 degree. This means your ms is less than equal to 1.93. So that means to guarantee both gain margin max greater than equal to 2 as well as phase margin greater than equal to 30 degree, what should be your here limit? Ms should be ultimately less than 1.9. Okay, so that means by if you design a system which will have for which ms is less than 2 approximately, then you can then you can guarantee that the system will have gain margin greater than equal to 6 dB and phase margin greater than equal to 30 dB. That you can always guarantee. Okay, so that means this is the relation among gain margin, upper side gain margin and phase margin and sensitivity norm. ms is nothing but the peak value of the sensitivity function, sensitivity frequency response of the sensitivity. Okay, so in this way, that means ms is a good indicator. That means if you can keep ms small, then a desired range of gain margin and phase margin you can also attain. So now the proof of this one, proof of this inequalities we will do. So I am considering a typical Nyquist plot, but it can be proved. The proof is same for any Nyquist plot. Okay, it doesn't matter. So I have considered the Nyquist plot of a loop transfer function is to be like this, or polar plot. Polar plot I have drawn. So this is a polar plot of a loop, suppose. Okay, and then what is and this is the unit circle I have drawn. Okay, my drawing is not that much perfect. Unit circle, and obviously this is the sensitivity circle, and the distance from -1 point to the lowest to this point is distance of the minimum distance of -1 point, and the Nyquist plot is ms inverse. That's the ms inverse. So I have drawn this MS circle such that this 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 becomes this just the Nyquist plot just touches this MS circle. Okay, MS inverse or sensitivity circle, S circle. So this is unit circle, and this is your S circle, and this is your uh, Nyquist plot. Okay, naturally. So this is your gain cost of frequency. This is your phase cost of frequency, and this is your this whole angle is your phase margin phi. Okay, and what is your gain margin max? So this is the inverse of this distance is your gain margin max. So 1 by gain margin, so, that means this distance here to here is your 1 by gain margin max, 1 by GM max, that I have written. So just I have named these points O, A, B, C, and D. So this is a point such that OD equal to DC. That means this angle is phi by 2. This angle is also equal to phi by 2. Okay, so this is a Nyquist plane. That means this is LS plane, LG omega plane. So a real of LG omega and imaginary of LG omega. Or x-axis is real of LG omega and y-axis is imaginary of LG omega. So now from this figure, what you can see that this OA is always greater than or equal to MS inverse, right? This distance OA is always greater than equal to MS inverse. So that I have written. Actually, it should be greater than equal to. Okay, I will correct it. OS is greater than equal to MS inverse. So what is OA? OA you can easily see. OA is what? Here to here is 1. So 1 minus and here to here is 1 by GM max. So that's why 1 minus 1 by GM max is greater than equal to sin I. I forgot to give. So it should be greater than equal to 1 minus 1 by GM max is greater than equal to MS inverse. Okay. So this implies your GM max is greater than equal to MS by MS minus 1. So that the one inequality we have to. Okay. So now if you consider this triangle, OBC triangle, okay, this triangle if you consider, now you see OC, this OC is always greater than equal to MS inverse because MS is this distance here to here. So OC is always greater than equal to MS inverse. So this means OC by 2, that means equal to OD. OC by 2 is greater than equal to 1 by 2 ms. Now OC by 2 means OD. So now what is this angle? So this is 90 degree. Okay, this is 90 degree. So what is OD? OD by OB. OD by OB is equal to what? Sine of pi by 2. Okay, so OD equal to OD, sorry, OD, so this is 90 degree. So OD divided by OB equal to 1 unit circle. So OD equal to, you can write then OD equal to sine of pi by 2. So that we have written sine of pi by 2. So this is greater than equal to 1 by 2 ms. So from there you can get phi is greater than equal to sine inverse 1 by 2 ms. Okay. So that means this is your phase margin inequality and this is your upper side gain margin inequality. Have you understood? If you have any doubt, you please ask me. Okay, so this is your proof of the inequality. So now we will discuss what is your what is the inequality for. So this here I have discussed your upper side GM. Now lower side, what is the inequality for lower side GM? Similar kind of inequality should also be there. So now we'll discuss lower side GM inequality. Lower side inequality. Yeah. So 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 these two we considered already. Gain margin max is this one and phase margin is this one. Now gain margin mean, that means lower side gain margin is, you can prove that ms by, it is lower side gain margin is less than equal to ms by ms plus 1. So how you can prove? So so I have considered a diagram, Nyquist plot, where both positive side gain margin and negative side gain margin is there. Here positive side gain margin was not needed anyway. So I have drawn a diagram. I have considered a Nyquist plot where both are there. In fact, using this single Nyquist plot, you can prove all three together. That's not the problem. Okay, because here gain margin mean is there, gain margin max both are there. So using this plot, you can prove all three. Anyway, already we have proved these two. So now this you have to prove. So from this plot, you can easily see, as I said, as I already said, this distance to this distance is 1 by gm max, and this distance to this distance will be 1 by gm min. Okay, one example we already considered whose Nyquist plot is like this in the last class in fact, yesterday. Okay, so so this distance is 1 by gm min and this distance is 1 by gm max. And what is your your circle? ms circle. ms circle will be like, will be this one now. Sensitivity circle. Okay. So from this figure, what you can write? You can write that this distance here to here. What is this distance here to here mean? The distance from this point to this point equal to what? 1 by gm min minus 1. Here to here distance is 1. So 1 by gm min minus 1 is greater than equal to ms inverse, because ms is this one. Okay. So at least it will be ms equal to ms inverse. So gm min minus this one equal to this distance, and this is greater than equal to this distance, that is equal to ms inverse. So from here directly you can show that gm min is equal to less than equal to ms by ms plus 1. Okay. So in Ulovich book, this gm min you will not get. Okay. From Ulovich book or any other book, any other book means in Ulovich book it is there. This inequalities, but this GM mean inequality you will not get, because they have considered only single gain margin. A GM mean inequality I have got from a paper, automatic control paper. Okay, so whatever information I got, I have shared it here. Okay, so as I said, now suppose you want to have a GM mean less than equal to 0.5 or GM mean less than equal to minus 6 dB. So now what should be your ms then? Ms by ms plus 1 is less than equal to 0.5, and then you can say that ms less than equal to 1. So that means if you want to have GM mean less than 6 dB, your ms has to be less than or at least equal to 1. Okay, at most equal to 1. So now, as I said, that for a we for a practical design, we normally consider ms is less than equal to 2. Why? That also we saw that it will guarantee positive side gain margin greater than equal to 6 dB and phase margin greater than equal to 30 dB. And this is a very good information. Okay, most of the practical system nowadays, aerospace in aerospace industry, they follow this limit very much. That ms, the sensitivity peak should be the design controllers such that earlier they used to design controller just based on gain margin and phase margin specifications, but but after a lot of study and many failures, so they saw. So this is an important yeah, for measure for robustness. So ms less than equal to 2 they consider. So now ms less than equal to 2 you can easily verify that ms less than 2 will guarantee that gain margin minimum, that means yeah, gain margin reduction of 2 by 3, minimum loss side gain margin of 2 by 3. Okay, that means lower side gain margin. So suppose your nominal gain is 1, you can reduce it up to 2 by 3. Okay, and already we saw that ms less than 2. Again, I am saying that upper side gain margin can be greater than 6 dB. That means you can amplify the gain, increase the gain by a factor of 2. That means ms less than 2. With ms less than 2, you can increase the gain by a factor of 2 at least, and reduce the gain by a factor of 2 by 3. Okay. Well, so we have considered, so far we have considered some robustness measure for uh, robustness measures again if there is parametric uncertainties. MS particularly handles uh, robustness against parametric uncertainty well. Okay, because as I said, that MS inverse is the distance, minimum distance of the Nyquist plot from -1 point. So as we can make the distance more and more, it will be good from robustness point of view, and at least we want MS less than 2, that we also saw. Now we'll switch
Hello,
to,
sir.
yes,
Sir,
yes,
actually, Shraddhara ma'am is in
waiting.
waiting lobby. She's not able to join.
Okay. So, I have added her as member, but why he is not joining as a member? Anyway, I have allowed her. Mm, mm. So, mm, yeah. Uh, now we'll discuss the new topic, that is robustness against unmodeled or neglected dynamics. So far, we considered robustness against parameter variations. Now, another source of important source of uncertainties is robust is neglected or unmodeled. So I discussed in the first class that uh, whatever topics I am teaching now, these are only for analysis. Okay, you have a controller, you have suppose design controller by some method. Some methods will teach. I'll teach you. Okay, you have designed some controllers. You have a plan. Okay, now you have design controller based on some that your controller, your loop has that ms less than 2 or not. Okay, or your loop has, so even if you have during the design you have not considered that MS and all those stuffs, but at least after designing the controller, before employing it to practical system, you should check whether your loop has at least MS less than 2 or not. Okay. Okay. Now we'll see what is the norm, what is the measure for robustness against unmodeled or neglected dynamics. So a simple example we will consider. Suppose the actual plant is as I was discussing this example, a simple system. Actual plant is a second order system, but we can easily approximate it to be a first order. That means here 10 by S plus 10 we have neglected. That may be your actual sensor dynamics. The sensor is much faster than the plant. So sensor dynamics, that may be, or maybe any other sensor dynamics means deliberately neglected, or it may happen that S plus 10, 10 by S plus 10 is a dynamics of some part which we could not model. Okay, that amounts for that amounts to unmodeled dynamics. Okay. So had is of first order of this thing. So now we want to determine what is the error. So we can easily obtain frequency response of this uh, of the error plan. What is the error plan? G hat minus G. Okay. So I can apply sine omega t. Both are stable. It doesn't matter. Uh, we can apply, no problem. Sine omega t. If we apply, then we will get the error dynamics error uh, error plot. Error also will be sinusoidal because these both are a linear system. Okay, so we can write EA equal to EA j omega. Okay, EA j omega equal to G hat G. So EA of j omega divided by uh, 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 what's called yeah, that means here if we apply sinusoid, it is a frequency response. If we apply sine omega t, then EA also will be sine omega t. And what will the amplitude of EA? Amplitude of EA will be this amplitude of EA, EA j omega. Amplitude of EA uh, will be just g hat of j omega minus g of j omega. That is this is coming from the concept of frequency response. Okay. So now EA j omega divided by G is what then? EA j omega divided by G will be this one. G hat j omega divided by G j omega minus 1. So EA j omega divided by G j omega ultimately will come out to this. Okay, so here there is a mistake. It should be 1000. Okay, it should 10 or it is 1, right? Oh, sorry, it should be 1. It should be 10. Yeah, G had to have 10, so it should be then 100. Okay, so there is a mistake. So that I will rectify in the PDF version when I will upload it. Today I will upload. So if you plot it now, this normalized error transfer function, a normalized error, if you plot it, frequency response of normalized error, what will the frequency response, magnitude response of normalized error, magnitude response of normalized error will be like this. So you can see that as frequency, so this is your cutoff 3 dB cutoff frequency equal to 10 radian per second, that you can see from this transfer what's called magnitude omega square, omega divided by root under omega square plus 100. So CD frequency is 1 by root 2. This again the corresponding frequency is 10 radian per second. Okay. So you can see that as frequency increases, your magnitude, that means error is more. Of course, error becomes constant after some frequency. So one thing we can say that as the frequency is much small compared to 10 radian per second, so the error is small, and as it is high, as the frequency is more than 10 radian per second, what is happening? The error is more. Yeah, the error is more. So that means what is the conclusion? Conclusion is neglected or unmodeled dynamics are dominant at high frequency. So low frequency, so neglected or unmodeled dynamics are prominent at affect much at high frequency. Low frequency, their magnitude is very small. Okay, we can neglect that. So it will not affect the system as such. But the error is more at high frequency. So this is the conclusion. Neglected or unmodeled dynamics are dominant at high frequency. So in general, what do we do? So the plot may be like this. So here I am getting a smooth plot because I have considered this is a very simple system I have considered, and the normalized error transfer function is nice. But it may happen that normalized error transfer function is of higher order. It may have many zeros, many poles. Okay, so it may look like this. We'll see that we'll see such kind of haphazard plots of normalized errors soon in an example. Okay, that we'll see. So it may happen. This the your normalized error plot is like this. So one thing is sure that this normalized error plot, you can consider some weight WC such that it encompasses the error. That means this weight plot is just above this this, this normalized error. Okay, so that you can do for any unmodeled dynamics, any normalized error due to unmodeled dynamics. If you do that, then then what you can write? So EA j omega divided by G of j omega equal to, so this was already there. So this is now what you can write. This is now less than equal to this error, this normalized error plot is equal to this. So now this is less than equal to what? Mod of WCJ omega, right? This is less than equal to mod of WCJ omega. So now if I want to make it equal to something, that means your delta j omega should be less than equal to 1. Otherwise it will not be less than equal to WCJ omega, right? So I have made it equal where delta j omega is less than equal to 1 for all omega. Okay. So now from this concept, what we can write? What is my Gj omega? Gj omega is the nominal plant. Means after neglecting your the unmodeled, after neglecting the dynamics, undesired dynamics, or after the simplified plan. Okay, G omega is a simplified plan, and what is G hat G omega? G hat G omega is the actual plan where all, if you do not consider, if you do not neglect any dynamics, so that means it is a transfer function of the true plant. G hat S is a transfer function of the true plant, so our actual plant. So the transfer function of the true plant, you can following this equation, the transfer function of the true plant, you can represent like this: G hat S equal to G hat S divided by Gs minus 1 equal to delta S into WCS. So if you from that you can write G hat S equal to Gs into 1 plus WCS into delta S. Here all are scalar, so it does it better. I'm just shifting this one. Okay, for MIMO system also you can write similar kind of thing. That MIMO systems is not in a syllabus. I'm not considering that, but you can easily extend it. It will remain same all the things. Okay, so where delta j omega is less than equal to 1, okay, for all less than 1, because your your this normalized error plot should just below WC. Okay, so delta j omega is less than 1. So here it should be actually less than 1, not less than equal to. It should be less than 1. Okay, so this model, so this is the model of the so this is your uncertainty. This is a particular uncertainty model. Okay, so what? So we have we have encompassed the uncertainties below WG omega plot. This is called uncertainty weight, WCS. So you can easily see that WCS is a high pass filter, right? So uncertainty weight, it is a high pass filter. So WCS is a high pass filter. So that designer has to consider which will encompass the neglected dynamics or unmodeled dynamics. So that means if you have neglected dynamics or unmodeled dynamics, you should know that what is the peak value of the uncertainty plot, error, normalized error. That you must know. That means normalized error plot, frequency response at least you must know. That you can easily have because using this figure you have your true plant, actual physical plant, and you have your approximated plant. And if you get the error experimentally, okay, then experimentally if you apply sinusoid and then if you get EAJ omega EA plot, then experimentally you can easily get this kind of curve, right? This kind of plot. Experimentally you can always have. And once this kind of plot you have, a designer can determine what is WCS or WCGM. Okay, just to encompass this uh, your normalized error dynamics. Okay, so this is very important model. G hat S equal to GS into 1 plus WCS into delta S. Now we will see what is the condition for robust stability. That means robust stability means here what? I have designed controller for the simplified plant. Now under which situation I have designed controller for plant GS. Now under which situation if I employ the controller for the two plant GHS, still the system remains stable. Okay, that is the problem. That we have that condition we have to find. Again, I am saying I have because I have simplified the plan, right? I have a simple plan GS. So I have designed controller for that using some method. Now what you have to do? I want to employ the controller for the true plan because I have to employ it is a physical plan. GHS is the physical plan. I have to employ the controller for the physical plan. Okay. I have employed the controller for the physical plant or true plant G hat S. Now I have to obtain condition in terms of GS and CS. CS means controller, such that even if uncertainty is there, that means the true plant is G hat S, still the controller CS can stabilize G hat S. At least the closed loop system will remain stable. So, so how to proceed? So as I was saying, so this is your true plant, true feedback, because it is your controller, CS is your controller, and I have employed that controller for the true plant, and but I have designed CS for only GS. I have not designed CS for GHS. Okay, because in GHS many terms are unknown. I have I have not designed CS for GHS. I have designed CS for GS nominal plant. But under which situation the stability of this one will also guarantee stability of this loop. That you will find. Okay. So here, what is your actual loop transfer function? What is the actual loop transfer function? So actual loop transfer function is your L hat S, because this is your actual system. This is your actual system. What is your actual loop? Loop means loop transfer function G hat S, or open loop transfer function G hat S into CS. Okay, so that you can write like this. Now G hat S is what we have already got, that G hat S is equal to GS into 1 plus this one. So if you substitute that, then G hat S you can write like this, and CS is your controller. Okay. So then L hat S you can write like this, because GS into CS is your LS, that is a nominal loop transfer function, that means loop transfer function of this feedback system, approximated feedback system. So that's why G into C equal to L, that you can write into 1 plus WCS into delta S. So again, what you can write, L hat S equal to LS plus this one delta S into LS into WCS. Okay, so that means now I want to, what I want to do, I want to plot. Suppose LS is known, a Nyquist plot or polar plot of LS is known. Then I want to see what is the polar plot of L hat S. Okay, so you can easily see that this is the addition. So what is the magnitude of this one? So you can always see that the magnitude of this one is less than equal to WCS into WCG omega, because the mod of this one you can always write less than equal to mod of this into mod of this. Now mod of this delta G omega mod is less than equal to 1. That's why your mod of delta J omega into L J omega into WC J omega is less than equal to mod of WC J omega into L J omega. So that I have written, I think, somewhere. Yeah, that is the concept. Okay, if you, so now suppose this is your L J omega plot. This is your L J omega, that means nominal loop or approximated loop transfer function plot. This is omega equal to 0, this is omega equal to infinity. Now what is the perturbation? Here Lj omega is no at every frequency omega, say at omega equal to omega 1, say for example. At omega equal to omega 1, so this is your Lj omega vector. This is your Lj omega 1. So now around that you have some uncertainties. And what is the magnitude of uncertainty? WCj omega mod of WCj omega. And magnitude of uncertainty is less than equal to mod of WCj omega and Lj omega. So that's why I have drawn a circle around this 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 Lj omega point. We so so what you can do, what you can say, what is L hat j omega 1? L hat j omega 1, L hat j omega 1 can lie anywhere in between around this circle. It may lie here, this point L hat j. This point is L hat L j omega 1. So L hat j omega 1 can lie anywhere. Okay, in this disc, inside this disc. Okay. Similarly, if you consider another frequency, L hat j omega 2, say, it may lie anywhere. Similarly, now you can see that this disc size, so as the frequency is small, this disc size will be less because this is a high frequency, as we have already seen, that the magnitude of the perturbation area of called error is more at high frequency. So error is more at high frequency, so that's why this disc radius, size of the disc or radius of the disc will increase as frequency increases. So it will be maximum at omega equal to infinity. Although I have not drawn it, I could have drawn a bigger disc here. Okay, so I have tried to show here that the disc size is increasing as frequency increases. So now what is the condition for stability? Condition for stability is here. That means it should not touch the L hat g omega should not touch -1 point. Okay, forget about encircling it. Even it should not touch -1 point. Okay, so what is the condition for that? You can easily see what is the disc. Yes, what is mm, what is the distance from -1 point to the nominal loop? That is 1 plus L omega, that I have already, that we have already seen. So the distance from -1 point to this point, because this is 1 and here to here is L omega. So this distance is 1 plus L omega, 1 then plus L omega. So here to here distance is 1 plus L omega. Now what is the distance from here to here? Distance from here to here is mod of, as I said, mod of WC j omega and L j omega, right? Distance from here to here is 1 plus L j omega, and distance from here, this radius of the disc, distance from here to here, that is the radius of the disc, is WC j omega mod of WC j omega into L j omega. So that means for robust stability, what condition you should have? This radius, this radius of the disc should be less than this distance. Otherwise, what will happen? If it is just equal, then this point will touch this one, this minus one. So that means 1 plus L omega should be greater than this disc, the radius of the disc. That means 1 plus L omega should be greater than L omega into WC omega, because L omega and WC omega is the radius of this disc. For all omega, for all such discs, this should happen for all discs. Okay, so for all omega. That's why it is. So this means Lj omega into Wcj omega divided by 1 plus Lj omega should be less than 1. So now it has very interesting property. So Wcj omega into, now I will denote Lj omega divided by 1 plus Lj omega as Tj omega. Okay. So Ts equal to Ls by 1 plus Ls. So it is known as complementary sensitivity function. So sensitivity function is what? 1 by 1 plus Ls, and complementary sensitivity means 1 minus sensitivity. Okay. So that means your robustability condition for robustness against unmodeled dynamics is here this one, Wcj omega into Tj omega should be less than 1. Okay. So that means what? From here you can write that Tj omega, your complementary sensitivity plot should be less than, that means complementary sensitivity plot should lie below 1 by Wcj omega plot. This is a very important thing. As I said again and again, even if you do not design uh, robust controller during the design process, but you should post check this. You have designed a PD controller or PID controller or lag lead controller, whatever it is. So before employing them to practical system, you should check that whether this condition is satisfied. So you can also design the controller even in the design process. You can consider these constraints in the design process also. That is taught in advanced control courses. That is known as H infinity control or those things. So that I am not going into. That is not there in your syllabus. But at least my suggestion is that for any practical system, after designing the controller, at least you should verify these things. Tj omega should lie, whether it is lying below 1 by Wcj omega. And given a system, how to determine Wcj omega, that I have already said. And Tj omega depends only on your plant and controller, nominal plant and nominal controller. And that means Tj omega is just Gc by 1 plus Gc. Okay. So that you can verify easily. In fact, we'll consider some examples. So the main important fact is that uh, here I have pointed out. So from this what we have got, that your Tj omega at high frequency, for if there is neglected dynamics or unmodeled dynamics, then at high frequency what you should have, at high frequency your Tj omega should be as small as possible, because this Wcj omega magnitude, this Wcj omega magnitude is 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 dominant. Okay. So Wcj omega, here it is written. So Wcj omega is dominant at high frequency. Okay. So therefore your Tj omega should be as small as possible at high frequency, because these are high frequency, neglected dynamics are of high frequency in nature. So for to ensure robustness against neglected dynamics, your Tj omega should be as small as possible. But Tj omega you cannot make small at all frequency, because you can see Tj omega is L by 1 plus L. So 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 Ls is of low pass behavior. So Tj omega will be equal to 1 at low frequency. So low frequency you cannot T j omega you cannot make less than 1. But what we can do, we can make T j omega small at high frequency, which is important in order to have robustness against neglected dynamics. So that I have written here. Okay. So in fact, you can see that how you can make T j omega very small at high frequency. So T j omega you can make small at high frequency if ls is made small at high frequency. Okay. So ls, again another thing is important, that ls has to be ls has to be large at low frequency in order to have sensitivity low at low frequency. Okay, so the loop plot will be like this, at least uh, high gain at low frequency and then low gain at high frequency. Okay, so again I am saying this is high gain at low frequency is needed. So high gain at low frequency is needed in order to have low sensitivity. Okay, again in order to have low uh, complementary sensitivity value, we should have low gain at high frequency. Okay, so that's why for a practical system, the loop behavior should look like this. This is your gain cost of frequency. Okay, at low frequency high gain and at high frequency low gain. Even it should be minus 40 dB per decade, or even higher. Okay, so in order to have least effect of the neglected dynamics. Okay, but we'll see if you use a PD controller or PID kind of controller. So you will see, or even okay, state feedback control you do not know. So if you use PD or PID kind of controller, the problem is there that this high frequency roll off rate in that case in those with those controllers reduces a lot. It will be maximum minus 20 dB per decade. Okay, because of derivative action. Okay, the PD controller, you will not be able to get this kind of minus 40 dB per decade roll off rate. As a result, what will happen? Those PD controllers or PID controllers are more prone to uh, means may exhibit those PD and PID controllers may exhibit less robustness in presence of neglected damage. That's why that with PD and PID controllers, we will also discuss that they are very prone to noise because 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 their the high frequency roll off rate is even with filter. I am saying it is minus 20 dB per decade. Okay, so those things we'll discuss slowly, but the loop behavior should be like this for any practical system: low high gain at low frequency, and then low gain at high frequency. So high gain at low frequency is needed in order to have low sensitivity, because S is 1 by 1 plus L. Okay, so L should be high because L is always low at low frequency because of low pass behavior, high frequency because of low pass behavior in nature. So this high peak, high gain at low frequency is needed in order to ensure less sensitivity, and low gain at high frequency is needed in order to have less complementary sensitivity. Peak. Okay. So now, so far, have you understood? If you have any doubt, please tell me, because these are very fundamental things. Then we'll discuss some examples. If you have any doubt, you can ask me. Do you have any doubt? If you have any doubt, please ask me. Okay, so we'll wait for 2-3 minutes. Just I am coming after. Just I will join after 2-3 minutes. Okay, I will stop for the time being recording. Okay.